we'll be going through the DeepSeek-V4 paper, and just trying to understand why they did what they did and how they did what they did. All right, so from the title, you can kind of tell, you kind of get an idea of what it is, like what one of their major goals is in the paper. Um, from the title, it says towards highly efficient million token context intelligence. So one of the biggest things that they're working towards in this paper is to develop a model that can efficiently process a million tokens of context. And so we'll see as we go through this paper, we'll see like the tricks and stuff that they use to do this. So it says that in this paper, they present a preview version of the DeepSeek-V4 series, including two strong MOE models, DeepSeek-V4 Pro with 1.6 trillion parameters, with 49 billion parameters activated during the mixture of experts forward pass inference, and DeepSeek-V4 Flash with 284 billion parameters and 13 billion of those parameters activated during the forward pass. So they both support a context length of a million tokens. And so their major technical contributions are, according to the abstract, a hybrid attention architecture that combines compressed sparse attention and heavily compressed attention. They also use manifold constrained hyperconnections. They also train both models on more than 32 trillion high quality tokens during pre-training, and then they do post-training to give the model like its agentic capabilities. So another important thing is that they say here that in the million token context setting, DeepSeek-V4 Pro requires only 27% of single token inference flops and 10% of the KV cache compared with DeepSeek-V 3.2. So as compared to their previous best model, this model is more efficient, like it requires 27% of the flops that the previous model did, and it uses a smaller KV cache. So means that like it's much more efficient during inference. Right. So the paper is split up like this. So it has the introduction, the architecture. It talks about the infrastructure that they use to train. It talks about pre-training and post-training. So in this session, I plan to talk through sections 1, 2, 4, and 5, because those are the sections that actually give you the important information about the model. The infrastructure section, it is somewhat important, but it doesn't really tell you anything about, it doesn't tell you anything like algorithmically about how the model was trained. It's more of like an engineering section where they detail the things that they had to do to make really large scale training and inference work for a model like this. All right. So starting with the introduction, right? So this first paragraph is kind of filler, but starting from the second paragraph, it says, in order to break the efficiency barrier in ultra-long context, they developed DeepSeek-V4. And through architectural innovations, DeepSeek-V4 X series, the DeepSeek-V4 series achieves a dramatic leap in computational efficiency for processing ultra-long sequences. This breakthrough here enables efficient support for a context length of 1 million tokens, ushering in a new era of million length context for the next generation LLMs. So Down here in the third paragraph, compared with DeepSeek V3, DeepSeek V4 retains the MOE framework and multi-token prediction while introducing several key innovations in architecture and optimization. So, to enhance long context efficiency, they design a hybrid attention mechanism that combines compressed sparse attention and heavily compressed attention. So, the compressed sparse attention compresses the KV cache along the sequence dimension and then performs DeepSeek sparse attention. And while heavily compressed attention applies a more aggressive compression to the KV cache, but keeps the dense attention. So, to strengthen modeling capabilities, they incorporate the manifold constrained hyperconnections. And those, they say that those upgrade conventional residual connections. Additionally, they introduced the muon optimizer to the training of the DeepSeek-V4 series, which leads to faster conversions and improved training stability. Right. So they then go on to say that by employing the hybrid attention mechanism with CSA and HCA, along with precision optimizations on computation and storage, DeepSeek V4 achieves significantly lower inference flops and substantially reduced KV cache size compared to DeepSeek V3.2. Same thing that we saw in the abstract. And during pre-training, they trained DeepSeek V4 on 32 trillion tokens and DeepSeek V4 Pro on 33 trillion tokens. Then after pre-training, the two models can natively and efficiently support 1 million length contexts. So, this provides a summary of the core evaluation results. So, in assessments of broad world knowledge, DeepSeek V4 Pro Max, the maximum reasoning effort mode of DeepSeek V4 Pro, significantly outperforms leading open source models on the Simple QA and Chinese Simple QA benchmarks. And then regarding educational knowledge, evaluated via MMLU Pro, HLE, and GPQA, DeepSeek V4 Pro Max shows a marginal lead over its open source counterparts, and it significantly closed the gap with leading proprietary models Gemini 3.1 Pro, despite still trailing in knowledge-based evaluations. And then for reasoning, through the expansion of reasoning tokens, DeepSeek V4 Pro Max demonstrates superior performance relative to GPT 5.2 and Gemini 3 Pro on standard reasoning benchmarks. Nevertheless, its performance falls short of GPT 5.4 and Gemini 3.1 Pro, suggesting a developmental trajectory that still trails state-of-the-art frontier models by approximately 3 to 6 months. Furthermore, DeepSeek V4 Flash Max achieves comparable performance to GPT 5.2 and Gemini 3.2 Pro. For agentic results on public benchmarks, DeepSeek V4 Pro Max is on par with leading open source models such as Kimi K2.6 and GLM 5.1, but is slightly worse than closed frontier models. In terms of long context, it delivers strong results on synthetic and real use cases with a 1 million token context window, surpassing Gemini 3.1 Pro and academic benchmarks. And when they compare DeepSeek V4 Pro with DeepSeek V4 Flash, they said that the Flash exhibits lower performance in knowledge evaluations, which is expected due to its smaller size. However, it achieves comparable results on reasoning tasks when allocated a larger thinking budget. So that's also expected. Like, to get a similar performance out of a smaller model, you need to allow it to think for longer, basically. So going on to section 2, the architecture section. So overall, DeepSeek V4 still retain the transformer model generally, and the multi-token prediction models that it had used previously, while introducing several key upgrades over DeepSeek V3.2. So they say, firstly, they introduced the manifold constrained hyperconnections to strengthen residual connections. They also design a hybrid attention architecture to improve long context efficiency. And then they employ the muon optimizer for the mixture of expert components. And let's see. They say for the mixture of expert components, they still adopt the DeepSeek MOE architecture with only minor adjustments from DeepSeek V3. The multi-token prediction remains identical to that of DeepSeek V3, and all other unspecified details follow the settings established in DeepSeek V3. So they're assuming that you have some knowledge of the DeepSeek V3 paper itself. But they do go into talking about the design decisions that they inherited from DeepSeek V3. So at a really high level, they inherit the mixture of experts and the multi-token prediction. So the DeepSeek here, so they inherit the mixture of experts and the multi-token prediction. But since we're here to talk about the V4 paper, I'll talk mostly about the new things that they've implemented rather than going over the DeepSeek V3 stuff. So the first thing that they do is they talk about the manifold constrained hyperconnections. So if you read this paper, like from here, where they're talking about the architecture itself, like the hyperconnections and the hybrid attention further down. It's very mathy and hard to understand. So rather than going through it step by step, I'll try to explain the intuition behind what it is that they were doing. So they start off by talking about standard hyperconnections. But since they introduce these manifold hyperconnections to replace the residual networks, I'll kind of start from the residual networks first and then try to go into the hyperconnections and then the manifold constrained connections, right? So um, visually, right, you have like a set of layers, right? Uh, you have a set of layers going through a model. So this is the input and this is the output, right? The input to a layer and pass it to the output of a layer, essentially. And they do this layer by layer. So each layer will kind of have a connection that skips around the layer itself and goes to the output of the layer, right? And so that will go on and on throughout the model itself. So at a high level, that's what a residual connection is. It was introduced to kind of allow models to allow them to make it easier to train really deep neural networks because with when you're training really deep networks, as the information flows through the network and the gradients flow back, the gradients can kind of become smaller and smaller over time, the further back it has to go. So by introducing these skip connections, the gradient had a direct path to flow back to the input in a sense, and then they wouldn't be diluted in a sense. So that was the idea behind residual connections. So the difference between these and like a hyperconnection. So if I have the same model, if I have the same model where information is flowing from input to the output, what a hyperconnection is that instead of just flowing to the output of the layer in front of it, it will also flow to the output of all the layers in front of it. And this will happen here as well. So here it will flow here and there, and then here it will flow down here. So um, this was introduced because these hyperconnections were introduced because um, the because like intuitively, who's to say that the information at this point of the network isn't important to the decisions that are made here, right? So if you only use residual connections, then the decisions that are made like two layers apart might not be um, made with all of the context that they need necessarily. So the hyperconnections were introduced um, to kind of counteract that problem. But the problem with the hyperconnections is that the hyperconnections are how do I say it? They're kind of unconstrained. So the during optimism, so yeah, so the hyperconnections are kind of unconstrained. So some of the connections might be stronger than they should be. So this layer up here might have a stronger influence on this layer than it needs to have because there's no constraint on the connection to tell it like, hey, you should only be influencing the layer this much, and you should only be influencing this layer that much. So the manifold hyperconnections try to solve that problem. So let me redraw this with the manifold hyperconnections in mind. So as we starting over, taking input from there, then we go to the next layer, then we go to the next layer and the output. So if you have the input and you have the output, you still have the hyperconnections, right? So I'm only going to draw this one set of hyperconnections just so that it's less messy. But you can think about the the difference with the manifold hyperconnections is that it's kind of like there's a learned um, constraint on these connections that tell it that give each connection like that weights each connection almost. So like the sum of the strength of each connection has to add up to one each time. So during training, the model will learn that the connection between the first layer's input and the first layer's output should only be like 20% strength, right? And then the first, well, it should only be like, let's call it 40% strength, right? Oops. Yeah, so it should only be 40% strength. And then the connection between this first layer's input and the second layer's output should only be 30% strength or 35% strength. And then the connection between first layer's input and the last layer's output should only be 25% strength. So when it does that, it kind of um, like the information still flows from each input to each output. So there isn't a so like information is flowing freely throughout the entire network, essentially. But we don't have the problem of one layer overpowering the other. like throughout training, the model will learn that the model will learn like how to weight the strength of each connection, and it will do that dynamically during inference. So you don't have to. So it's not something that you have to think about. The model learns how to do that and takes care of that natively. So that's basically the idea behind the manifold constrained hyperconnections. Um, so uh, that is essentially what um, this section here, section 2.2 is trying to tell you, but it does it like in a very mathy way. Like research papers are written for, like the expectation with a research paper is that the reader is also an expert in the field. So they should know the math that you're talking about. But that kind of makes it a bit difficult for um, like someone who is less experienced to enter the field. Um, so in this like explanation, I kind of tried to distill all of that down in a more intuitive way. All right. So moving on to the next section where they describe the hybrid attention mechanism with the CSA and the HCA. So in this section, um, they say that they design two efficient attention architectures, right? So the compressed sparse attention and the heavily compressed attention. And they employ their interleaved hybrid configurations. So typically, when you hear the term interleaved, um, let's imagine that we have, um, again, multiple layers in a model, right? Um, so you have one transformer block, you have another transformer block, and then another transformer block. As far as I understand it, what they mean by the interleaved attention is that the attention in the first transformer block will be CSA, and then the attention in the second block will be HCA, and then the third transformer block will be CSA, and then the next one will be HCA. So it doesn't seem like the hybrid attention means that it's CSA plus HCA in a single layer. It seems to me that it's CSA and HCA interleave throughout the model rather than within a single layer. Um, but moving back to like a high level thing. So it says that CSA integrates both um, compression and sparse attention strategies. So, and then HCA just aims for extreme compression by consolidating the KV cache of every M dash tokens into a single entry. Right. So again, um, oops. So again, behind where I was. Sorry about that. Uh, yeah. So again, rather than going through line by line the really mathy explanations of like how they did this, I'll try to explain it a bit more intuitively. So um, at a really high level, with the compressed sparse attention, it works in two stages, right? So if we look at this diagram here, what it first does is it compresses the KV cache. Um, so instead of storing every token, so these are the state of every all the KV tokens, and then so instead of storing every token independently, the M tokens are compressed into a single KV entry, right? So the sequence length becomes smaller by a factor of M, right? And then after compression, there's like some selection of those KV entries. And that selection is done by like this lightning indexer block. So um so yeah, the compressed tokens, and so they start by compressing the tokens, and then of those compressed tokens, they use this lightning indexer to select some of those compressed tokens and um, send those to like a multi-query attention module, essentially. Um, so like at a really high level, you can think of it as like instead of, so these DeepSeek-V4 models, they have a 1 million token context. So instead of attending to each of the 1 million tokens, the CSA model or the CSA attention algorithm only attends to compressed semantic chunks of those million tokens. So each of those chunks will contain the information in um, probably some block of those 1 million context tokens. So they needed to do that to make the attention itself efficient. So the next attention module is the um where is it? The heavily compressed attention. Uh that is spoken about here, but it's described in this figure 4. Right. So the HCA, the heavily compressed attention, essentially just pushes the compression even further. So instead of CSA, where it basically did sparse attention over like some compressed blocks, the HCA just does really, really aggressive compression of the tokens. But it does like a dense attention kind of thing over it instead. Um, so yeah, so it will start by um it will like have the million tokens here, and it will just really heavily compress them. That instead of this million, you probably have like a fifth or like a sixth or something of those tokens. And then it will concatenate those with some KV entries that come from like a sliding window, and it will do like a standard dense attention on those compressed KV values rather than doing the attention on um, the the KV values of the entire context. So um, like why they do this in a hybrid manner is because like at a high level you can think of it like different layers would need information at different um, forms, different levels of granularity, I guess. So some layers will benefit from like the sparse retrieval like behavior of the CSA, and other layers will benefit from the coarse global summaries of the HCA. So when they interleave those CSA and the HCA blocks through the model, um, this lets them, this lets the model um, put the layers that need the retrieval, the sparse retrieval like behavior around the CSA attention, and then put the layers that need the global summaries around the HCA attention, essentially. Right? And then um, so after they do that, the next thing they talk about is the muon optimizer itself, right? So before muon, like the standard, well, for probably like 10 years, since around 2014, 2015 maybe. The standard optimizer that was being used in AI has been the Adam optimizer. Um, and then more recently, an improvement was made to the Adam optimizer called the Adam W optimizer. And so prior to the Muon optimizer, like for training um, every everyone essentially was using the Adam W optimizer. Um, but then recently, I think like in 2024-ish or early 2025, the Muon optimizer was developed. Um, and so the Muon optimizer, it at a high level um, improves training speed, it stabilizes the training, and it uses like some it uses like a Newton-Schultz orthogonalization strategy that um, kind of kind of helps to get better representations um, for optimization. However, um, the thing with the muon optimizer is that it can only be used for um, it can only be used for square matrices. So n by n or m by m or a by a matrices, right? So every component of the neural network that isn't a square matrix necessarily has to use another optimizer. So when you're using the muon optimizer um, for training, you're essentially using two optimizers over different sets of parameters. Um, so the um, so you can see here, they say that they use the muon optimizer for the majority of modules in the DeepSeek-V4 series due to its fast convergence and improved training stability. But they maintain the Adam W optimizer for the embedding module, the prediction head module, the static biases, the gating factors of the MHC modules, and the weights of all the RMS norm modules. So it says all other modules are updated using Muon. And additionally, they apply weight decay to the muon parameters. They use the Nesterov trick and rescale the RMS of the update matrix for reutilization of the Adam W hyperparameters. Right. Um, yeah. So let's see. Where are we? Hybrid Newton-Schultz iterations, avoiding exploding attention logics. Okay, so here they have the algorithm itself sketched out for the muon optimizer, right? So at a really high level, how it works is for each training step, and it will update weight by weight. So for the for the matrices with um, with the independent weights, they'll first compute the gradients and then they'll accumulate momentum buffers. They use this Nesterov trick that's outlined in this um, hybrid Newton-Schultz algorithm. And then they'll rescale the updated RMS, and then perform weight decay prior to updating the weights themselves. So this is the actual update that's done to the models themselves. But before you can do that update, there's a bunch of stuff that you have to actually calculate. Um, that's actually used to do the update itself, right? So that is, I think, it for the um architecture itself. They talk about the next section talks about the infrastructure. Um, but I'm going to skip that because that's not as important um for understanding how things work. So far we've gone through the introduction and the architecture sections, although we went through the architecture section at a pretty high level. So we'll be skipping the infrastructure section, but after that, we will be going to the pre-training and then the post-training sections. So, heading to pre-training, right? Where are we? Here we go. Pre-training. So, on top of the pre-training data of DeepSeek-V3, they endeavor to construct a more diverse and higher quality training corpus with longer effective context. So for data that they source from the web, they implement filtering strategies to remove batched auto-generated and templated content, mitigating the risk of model collapse. They use mathematical and programming corporal to they use mathematical and programming data, and they enhance the coding data of DeepSeek-V4 series by incorporating agentic data during the mid-training phase. So, generally, when you're training these models, these really long context models, what typically happens during pre-training is that pre-training is kind of broken up, as I understand it, into two phases, right? So there's the start of pre-training, where like you just start to train the model from scratch. But usually when you do that, you train it with like short context, like maybe 32K tokens or something like that. But then the second part of the pre-training phase is called mid-training, which they just mentioned here. And mid-training is when they increase the context length to the full million tokens and then continue the training. So they introduced the agentic, so that would make sense that they introduced the agentic um, they introduced the agentic data during the mid-training phase because you want the model, the million context token model, to have those agentic capabilities, right? Then it goes on to say that for multilingual data, you build a larger corpus for DeepSeek-V4, improving its capture of long-tail knowledge across different cultures. So what this is saying is that they're using more and more data from different languages to basically get DeepSeek-V4 to be more comfortable speaking in languages other than Chinese and English. They go on to say that they place a particular emphasis on long document data curation, prioritizing scientific papers, technical reports, and other materials that reflect unique academic values. Combining all of the above, the training corpus comprises of more than 32 trillion tokens containing mathematical content, code, web pages, long documents, and other high-quality categories. So if you remember, the DeepSeek-V4 Flash uses 32 trillion tokens, and then DeepSeek-V4 Pro uses 33 trillion. So to kind of account for both of them, they just said that they use more than 32 trillion tokens there. So talking about the pre-training setup of each of the models. So for DeepSeek-V4 Flash, the model, this is where they describe the model architecture itself, right? So they set 43 transformer layers. So they set the number of transformer layers to 43, and the hidden dimensions has a dimension of 4096. For the first two layers, they use pure sliding window attention. For the subsequent layers, CSA and HCA are used in interleaved manners, with the interleaved being CSA is in one layer, and then HCA is in the next, then CSA, then HCA, blah, blah, blah. Right. So for CSA, they set the compression rate of M to 4, and then the number of indexer query heads to 64. The indexer dimension is 128, and the number of KV entries selected for sparse attention is 512. Right. So for HCA, the compression rate is 128. So you can tell, like for CSA, the compression rate was 4, and for HCA, it's 128. So you can tell that HCA has a much more aggressive compression being applied to the tokens. So for both CSA and HCA, the number of query heads is 64, and the head dimension is 512. The query compression dimension is set to 1024, and the number of output projection groups set to 8, and the dimension of each intermediate attention window is set to 1024. For the additional branch of sliding window attention, the window size is set to 128. They say that they employ MOE layers in all transformer blocks, but they use the hash routing strategy for the first 3 MOE layers. Each MOE layer consists of 1 shared expert and 256 routed experts, where the intermediate hidden dimension of each expert is 2048, and among the routed experts, there are 6 that are activated for each token. All right, and then with multi-token prediction, the depth is set to 1. And as for the manifold hyperconnections, the expansion factor, NHC, is set to 4. And the number of the sinkhorn knop iterations is set to 20. And under this configuration, DeepSeek-V4 Flash comprises 284 billion total parameters, of which 13 billion are active for each token. So in DeepSeek-V4 Pro, on the other hand, the total number of transformer layers is 61. The hidden dimension, D, is set to 7,168. So the first 2 layers in DeepSeek-V4 Pro, they use HCA, the heavily compressed attention. And then for the subsequent layers, CSA and HCA are used in an interleaved manner. So they say for CSA, they set the compression rate to 4, similarly to DeepSeek-V4 Flash. The number of index or query heads is set to 64. The indexer dimension is set to 128, and the number of KV entries selected for sparse attention is 1024. For HCA, the compression rate is set to 128, also similar to DeepSeek-V4 Flash. And for both CSA and HCA, the query head is set to 128, head dimension to 512, compression dimension to 1536. The number of output projection groups is set to 16, and the dimension of each intermediate attention output is set to 1024. For the additional branch of sliding window attention, the window size is set to 128. They employ MOE layers in all transformer blocks, but similar to DeepSeek-V4 Flash, they use the hash routing strategy for the first 3 MOE layers. So in DeepSeek-V4 Pro, each layer consists of 1 shared expert and 384 routed experts. So as opposed to Flash, which had 1 shared expert and 256 routed experts, where the intermediate hidden dimension of each expert is 3072. Among the routed experts, 6 experts are active for each token. So that's the same as in V4 Flash. The multi-token prediction depth is set to 1. And as for the manifold hyperconnections, the expansion factor is set to 4. The sinkhorn knop iterations is set to 20. So with this configuration, DeepSeek-V4 Pro consists of 1.6 trillion parameters total, of which 49 billion are active for each token. So, again, training setup, they use the Muon optimizer for the majority of parameters, but they use the Adam W optimizer for the embedding module, prediction head, the weight of all the RMS norm modules. For Adam W, they set the hyperparameters to these settings. And for mu1, they set the hyperparameters to these settings with the momentum of 0.95 and the weight decay of 0.1. They also rescale the RMS of each update matrix to 0.18 for reutilization of the Adam W learning rate. Like they've said before, they use 32 trillion tokens for training, and they employ a batch size scheduling strategy that increases the batch size in tokens from 75.5 million tokens. And well, yeah, from a small size, they increase the batch size from a small size of 75.5 million and then keeps it at 75.5 million during most of training. The learning rate, they said, is warmed up linearly through the first 2,000 steps, and then it's maintained at 2.7 times 10 to the minus 4 for the majority of training. Then near the end of training, they decay the learning rate 2.7 times 10 to the minus 5, followed by a cosine schedule. The training starts the sequence length of 4,000, and they gradually extend the training sequence length to 16,000, 64,000, and then 1 million, right? So that's what I was saying earlier. Like with the two stages of pre-training, you have the first stage and then the second stage. So in the first stage, you have it training with a really small sequence length. But then over time, during the mid-training stage, you increase it gradually up to the 1 million token so that the model can learn to handle that. Right. So they go on to say, for the setups of sparse attention, they first warm up the model with dense attention for the first trillion tokens, and then they introduce the sparse attention at the sequence length of 64K here. And then they keep the sparse attention during the rest of training. So when they introduce attention sparsity, they first set a short stage to warm up the lightning indexer in the CSA. So they set a short stage to warm up the lightning indexer in CSA, and then they train the model with sparse attention for most of the training. Then after that, for the auxiliary loss-free load balancing, they set the bias update to 0.001. And for the balance loss, we set its loss weight to 0.0001 to avoid extreme imbalance within single sequences. The MTP loss weight, multi-token prediction loss weight, is set to 0.3 for most of training and to 0.1 upon the start of the learning rate decay. Right. So for the DeepSeek-V4 Pro, it said that except for the specific values of hyperparameters, the training setup of DeepSeek-V4 Pro is consistent with DeepSeek-V4 Flash. So I won't go into that. But then they have a section about mitigating training instability, right? So they say that training trillion parameter MOE models present significant stability challenges, and DeepSeek-V4 series are no exception. They encountered notable instability challenges during training. While simple rollbacks could temporarily restore the training state, they proved inadequate as a long-term solution because they do not prevent the recurrence of loss spikes. So empirically, they identified that the occurrence of spikes is consistently tied to outliers in the MOE layers. And the routing mechanism itself appears to exacerbate the emergence of these outliers. So they said that the problem was outliers in the MOE layers, and the routing mechanism in the MOE layers appears to make these outliers happen more and more often. So therefore, they sought to tackle this issue from two dimensions. They sought to break the cycle induced by routing, and they sought to directly suppress anomalous values. Fortunately, they say that they discovered two practical techniques that maintain training stability. Um, they said that although a comprehensive theoretical understanding of their underlying mechanisms remain an open question for now, they are sharing these techniques openly to foster further exploration. So, the two techniques that they discovered are anticipatory routing um, here and swig-loop clamping. So, with the anticipatory routing, they said that decoupling the synchronous updates of the backbone network and the routing network significantly improves training stability. um, so at step T, they use the current network parameters data for feature computation, but the routing indices are computed and applied using historical network parameters. um, and at step T, oh, I see. So during optimization, they use the network parameters um, at different time scales. So during training, they'll continuously save um, the snapshots, let's say for example, every 100 iterations, right? So the most recent weights would be used to um, would be used for feature computation, but the routing indices would use weights maybe from like 500 um, iterations ago during optimization. And they said that to circumvent the overhead of loading model parameters twice, they fetch the data for step T in advance at step T minus delta T. And so because they're anticipatorially anticipatorily computing and caching the routing indices that will be used, that's why they call this approach anticipatory routing. So with swig loop clamping, they say that clamping has been heavily studied to stabilize training. Um, but in their training runs, they empirically found that by applying the swig loop clamping, um, they efficiently eliminate outliers and they substantially aid in stabilizing the training process without compromising performance. So throughout the training of both DeepSeek-V4 Flash and DeepSeek-V4 Pro, they clamp the linear component of Swiglu to the range of -10 to 10, while capping the upper bounds of the gate component at 10. Right. So, in terms of evals, for pre-training evals, they talk about it in terms of world knowledge, language understanding, and reasoning, and then coding and mathematical benchmarks. So here they talk about some of the benchmarks themselves that they included. So they use AGI for world knowledge. They use AGI eval. They use C eval, CMMLU, MMLU, MMLU Redux, MMLU Pro, MMLU, Multilocal, Simple QA, Super GQA, GPQA. They use Facts Parametric and Trivia QA. So here they're just listing um, the the benchmarks that they use, but I don't think that they expect you to know what each of those benchmarks is or what it's used for. So they kind of just say that these set of benchmarks are used for world knowledge, this set is used for language understanding and reasoning, and this set is used for coding and math benchmarks. Right. So if we go down, they also use like long context benchmarks down here. Long bench V3 V2. Right. So if we go down a bit, we'll see that in table 1, they provide a comparison of DeepSeek V3.2, DeepSeek V3.2 with DeepSeek V4 Flash and DeepSeek V4 Pro across all of these benchmarks, right? So as you can see, the so the best performance is going to be bolded. The second best performance is underlined. So you can see that V4 Flash and V4 Pro both substantially outperform DeepSeek V3.2 in world knowledge, except for Trivia QA, where DeepSeek V3.2 is better than DeepSeek V4 Flash. For language and reasoning, V3.2 actually has better performances than has the best performance here for the BBH benchmark. But for the rest of them, the V4 Pro base is the best performing one. And then for the code and math benchmarks, V3.2 performs best on Big Code Bench, and V4 Pro performs the best on most of them, which is expected, but V4 Flash performs the best on MGSM and CMath. With the and in the long context benchmark, V4 Pro performs the best. So overall, the results are basically what you'd expect, with V4 Pro performing the best overall, and then V4 Flash, and then V3.2. So after this, they start talking about how they did their post-training. So the post-training is arguably the most important section of the paper, because like we said earlier, the post-training the point of the paper is to unlock efficient long context capabilities, right? And then the post-training is where that really happens. So let's go through it. So they say that following pre-training, they conduct a post-training phase to yield the final models of the DeepSeek-V4 series. So although the training pipeline largely mirrored DeepSeek V3.2, a critical methodological substitution was made. The mixed reinforcement learning stage was replaced entirely by on-policy distillation. So they'll explain what that is later in the paper. So they start by talking about specialist training. So they developed domain specialists by adapting the DeepSeek V3.2 training pipeline. They said that each model was sequentially optimized through an initial fine-tuning phase and subsequent reinforcement learning guided by domain-specific prompts and reward signals. So, for the RL stage, they implemented the GRPO algorithm, the group relative policy optimization, maintaining hyperparameters closely aligned with prior research. Now they're saying that it's widely recognized that the model's performance and redoing tasks is fundamentally governed by the computational effort expended. So what that means is that the more time the more time the model spent thinking, the better their performance is. So that's why in ChatGPT, or if you ever used Codex or something like that, you'll have different reasoning efforts. So you'll have the low, the medium, the high, and the X high, where X high performs the best because it spends the most time reasoning. So how they get those is they say that they train distinct specialist models under different RL configurations to facilitate the development of models optimized for varying reasoning capabilities. So, as detailed in table 2 down here, DeepSeek-V4 Pro and V4 Flash support 3 specific reasoning modes. For each mode, they apply distinct length penalties and context windows during RL training, which result in varying output token lengths for reasoning. So, to integrate the 3 distinct reasoning modes, they use specialized response formats demarcated by think and the end think tokens. Furthermore, they say that for the think max mode, they prepend a special instruction at the beginning of the system prompt to guide the model's reasoning process, as shown in table 3, which is down here, right? So here they have the injected instruction. So they tell it explicitly that their reasoning effort must be the absolute maximum with no shortcuts. They have to be thorough in their thinking and they have to comprehensively decompose the problem to resolve the root cause, rigorously stress test logic against possible paths and edge cases. And they have to explicitly write out their deliberation process and to document every intermediate step, considering alternatives and rejecting hypotheses to ensure that there's absolutely no assumptions left unchecked. So, the next thing that they start to talk about are generative reward models. So they say that typically easy to verify tasks can be optimized through simple rule-based verifiers or test cases, while harder to verify tasks traditionally rely on RLHF or reinforcement learning from human feedback. They say that this necessitates extensive human annotation to train a scalar reward model. So in RLHF, something that's typically done is typically trained is called a reward model, where you'll have an input and then like the model will produce an output and then the reward model will get that out the model's output as input, and then it will tell you on a scale of 1 to 10, for example, how good the output is in terms of quality. Right? So in the post-training phase of DeepSeek-V4, however, they don't use those conventional reward models. Instead, to address hard to verify tasks, they say that they curate rubric-guided RL data and employ a generative reward model to evaluate policy trajectories. So they say that they use reinforcement learning directly on the generative reward model. So they say that they have an actor network that functions as the reward model, and that enables the joint optimization of the model's evaluation proficiency alongside its standard generative capabilities. It says by unifying those roles, the model's internal reasoning capabilities are inherently fused into the evaluation process, which results in highly robust scoring. They say further that this approach achieves superior performance with only a minimal set of diverse human annotations. And as the model leverages its own logic to generalize across complex tasks. So this is table 4, so that's what we're talking about next. So this is talking about how like tool calling and special tool calling tokens are essentially used to give the model access to capabilities that the model doesn't normally have. So if you want the model to, if you ask the model a question about weather, it has to call like a weather API, essentially, to get information about the weather that it can then give to you, the user, right? So this section talks about how they do the tool calling itself. So They say that consistent with our previous version, they utilize a dedicated think and stop thinking tags to delineate the reasoning path. In the DeepSeek-V4 series, they introduce a new tool calling schema that employs a special DSML token and uses an XML-based format for tool invocations, as demonstrated in table 4 up here. So, um, this is there's the schema that they use to call tools. So, when you call a tool, like this has to be the format that the tool call follows. Yeah, here. So from here to here. So they'll say, so this is the command that starts the tool call, and then you put in the name of the tool and the parameters that you're passing into the tool and stuff like that. Then any information that needs to go, any additional information that needs to go there, then they'll invoke it. They'll say they'll invoke the name of the tool again. And oh, wait, actually, no. So you have my mistake. So yeah. So you have the tool here. You invoke the tool name, you pass parameters to it, and then you end that tool call. Right. So here is where they're starting another tool call. They're invoking another tool name and having all of this stuff inside of it, and then they'll end the tool call itself. And after that is when they end the overall tool call itself. So it also says that string parameters should be specified as is and set to string equal true. For all other types, numbers, booleans, arrays, and objects, they should pass the value in JSON format and set string to false. If thinking mode is enabled, you have to output the complete reasoning inside the think inside the think tokens before any tool calls or final response. So in this diagram here, they kind of talk about how they interleave the thinking with the tool use. All right. So they spoke about the interleave thinking in the table above here. So this is like a visual explanation of how they do it. So when they're actually, let me read through this. Right. So in figure 7 here, they say there are two general scenarios that um, the there are two general scenarios that the AI model has to operate in when it has agentic capabilities. It has to operate when tools are required to be used, and also when there are no tools that are required to be used, right? So starting from the scenario where tools are not required, if you look here, um, the user would send a message to the model, right? The model will think for a bit and then answer, right? And that's turn 1. So the user would see this answer. Then in turn 2, the user would ask. So the question that the user asked in turn 1 is there as input. And then the answer that the model gave is also given as input to the model prior to the user's second message being asked, right? So they remove the thinking because the thinking, I guess, like they're trying to manage the context, so that the context doesn't blow up too much. And if the model is thinking for like 100,000 tokens before it outputs an answer to the user, um, the model only has 1,000,000 tokens worth of context. So they have to manage that context well before yeah, they have to manage that context well so that the context doesn't blow up and the user can get good answers. Right. So in the second turn, you'll get the user's message, the answer from the first question, and then the second message from the user. Then the model will think a bit and answer. Then in the third turn, you'll get message 1, answer 1, message 2, answer 2, and then message 3 from the user. After that, the model will just think for a bit again, and then output its final answer. Right. So in the tool calling scenario, things get a bit more nuanced up here. Right. So if you look closely at it, you'll see that there is turn 1.1, turn 1.2, and turn 1.3. So what that means is that so the user, so there's like that string that we spoke about earlier, the string schema, and then the user would ask their message, right? So the model will think about it, and because the user would ask something that the model can't do natively, the model will call a tool, which is done here, right? But it might not get the answer that it wants from that tool, or it could get the answer that it wants, but then it needs to call another tool. So when that happens, right, before the model calls the other tool, all of this is stuffed into the context here, 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 and here. And then it will also add the result of the tool call to the input of the context. And then the model will think some more, and then it might decide that it needs to call another tool. So when it does that, it will have the result from tool call from turn 1.1 and the thinking and the tool call and the tool result from turn 1.2. Then it will think a bit more and then give you your answer. So this all happens in a single turn. So what that means is that the user would ask a question, and then all of this happens under the hood, like within the model itself. And then in turn 2, it's just basically the same thing over. So it would stuff all of this into the context and then append the user's message. And then that cycle would happen over and over while the user is talking to the model. And so those two thinking paradigms are essentially outlined here in this interleave thinking section. So table 5 here kind of just talks about some quick instructions that the models will have. So for the quick instructions, they say that in chatbot scenarios, a number of auxiliary tasks, example, determining whether to trigger a web search or recognizing intent, have to be executed before generating a response. So they say usually these tasks are handled by a separate small model requiring redundant pre-filling since it cannot reuse the existing KV cache. So to overcome this limitation, they introduce quick instructions where they append a set of dedicated special tokens to the input sequence, where each token corresponds to a specific auxiliary task. And then by reusing the already computed cache, this mechanism avoids redundant pre-filling and allows certain tasks, such as generating search queries and determining authority and domain, to be executed in parallel. They say that this approach significantly reduces the user perceived time to first token, which means that to the users, from the user's perspective, it just seems like the model generates the tokens much more quickly. And it eliminates the engineering overhead of maintaining and iterating an extra small model. The supported quick instruction tokens are summarized in table 5. So these are the quick instruction tokens up here. So moving on to on-policy distillation. So they say that after training multiple domain-specific experts via specialized fine-tuning and reinforcement learning, they employ something called multi-teacher on-policy distillation as the primary technique for merging expert capabilities into the final model. So on-policy distillation has emerged as an effective post-training technique for efficiently transferring the knowledge and capabilities of domain experts into a single unified model. They say that this is achieved by having the student learn from the output distributions of teacher models on its own generated trajectories. So, formally, given a set of n expert models, the on-policy distillation objective function is defined here. So they say that in this formulation, Wi represents the assigned weight for each expert, typically determined by the relative importance of the expert. And then they compute the result KL divergence. And they say that that requires sampling training trajectories from the student to maintain on-policy learning. So essentially what happens here is, right, you'll have multiple expert models. So let's say you have so let's say, so let's say you have multiple expert models. So you have model 1, model 2, model 3. So let's say that this is an expert at physics, this is an expert at bio, and this is an expert at chemistry, right? And then you have your main model here. You have your main model here, right? So, and you want it to be an expert at both physics, bio, and chemistry, right? So what this loss does is it will say this Wi represents the weight of each expert determined by the importance of each expert, right? So for our physics question, for example, W1 would probably equal 0.9. W2 would probably equal 0.3, and then W3, 0.03, and then W3 would probably equal 0.07, right? So all of them would add up to 1. And what this DKL does, so the KL divergence itself, what it does is it essentially, at a really high level, it takes two probability distributions, and the closer those distributions are, the smaller the KL divergence is, right? So here, if you have DKL, and let's say you have distribution P and distribution Q, the KL divergence is equal to sum of P log P over Q, right? So if P and Q are equal, so if the two distributions are equal, then this ratio is equal to 1, and log of 1 is equal to 0, right? So that is, so essentially, like, so with this loss, you're trying to minimize the loss. So you're trying to make these two distributions, pi theta and pi ei, as equal, as close to each other as possible. So you're trying to minimize this loss overall, right? So if they're not equal, then the loss is not going to be equal to 1. I mean, it's not going to be equal to 0. And so you're constantly just trying to minimize and minimize this loss. You're trying to make this loss smaller and smaller to make these distributions closer and closer. So where those distributions come from would be, so pi theta would be the output of here, right? So you'd have pi theta, and then here you would have pi E1, here you would have pi E2, and here you would have pi E3, right? So you'd be trying to get this distribution pi theta as close as possible to each of these. And so what it will do, because the weight of this one is the biggest, like it will assign this one the most importance. So it will say that dkl of pi theta with pi e1, yeah, this one is the most important for this task because we're asked a physics question. So we need to treat the physics expert as the most important. You need to treat the physics expert as the most important. And so they'll be trying to minimize this loss over the more. They're treating the output of the physics expert as more important than the bio expert or the chem expert, if that makes sense. Right. Um, so, uh, moving on, it says that the underlying logic ensures that the unified policy selectively learns from specialist expert relevant to the current task context. Then, through this mechanism, the knowledge from the distinct expert weights is consolidated into a single unified parameter space. So, the knowledge from the physically distinct experts, so that would be 1, 2, and 3 up here, is consolidated into the unified parameter space, which would be model M here. Right. So, moving on, they talk a bit more about post-training infrastructure itself, right? So they say that the post-training infra is built on the scalable framework developed for DeepSeek V3.2. So they're saying that the infrastructure is supposed to enable efficient execution of ultra-long context reinforcement learning and on-policy distillation, merging tasks involving over 10 distinct teacher models, thereby substantially accelerating the iteration cycle for model releases. So, what are these infrastructure stuff that were done to enable the efficient execution? So the first thing was FP4 quantization aware training. The second thing was efficient teacher scheduling for full vocabulary on policy distillation. And thirdly, there was a preemptible and fault-tolerant rollout service. Fourthly, there was they scaled the reinforcement learning framework to the million token context, and then they sandboxed the infrastructure for the agentic AI. So, like I said earlier, the infrastructure stuff isn't as important for the for understanding how the model itself works. So I guess if there's interest in going through the infra itself, maybe we can do a follow-up session to this. But for now, I won't go through those. So I just pointed them out. So in case you're curious, you can go look it up yourself. But I won't be going through those today myself. Right. So the next thing they talk about is the benchmarking for the post-training. So for benchmarking, they think about they benchmark the knowledge and reasoning capabilities. They benchmark the million token context length. They benchmark agentic capabilities. Yeah, so and in each of these sections, they talk about the data sets that they use to actually do these benchmarks. So the knowledge and reasoning benchmark, they use MMLU Pro, GPQA, Humanities Last Exam, Simple QA Verified, Chinese Simple QA, Live Code Bench, Code Forces, HMMT, Apex, Apex Shortlist, IMO Answer Bench, and Putnam Bench. And then after that, they talk about how they did those benchmarking. So they said that for code, they evaluate the DeepSeek-V4 series on Live Code Bench V6 and an internal Codeforces benchmark. For Codeforces, they collected 14 Codeforce Division 1 contests, and yada, yada, yada. For the reasoning and knowledge tasks, they set the temperature to 1.0 and the context window to 8,000 for the non-think, 128,000 for the high, and 384,000 tokens for the max mode. So for each of the reasoning efforts, they gave them for the lowest reasoning effort, they gave it the lowest amount of tokens to be able to work with. And for the subsequently higher and higher reasoning efforts, they gave them more and more tokens to be able to work with. So the next thing they evaluated was the 1 million token context capabilities. They said that since DeepSeek-V4 supports 1 million token context, they evaluate performance in long context scenarios using OpenAI, MRCR, and Corpus QA as the benchmarks. They said that they reevaluate Claude Opus 4.6 and Gemini 3.1 Pro on these tasks with the goal of standardizing the configuration across all modules. They did not evaluate GPT 5.4 because its API failed to respond to a large portion of our queries. Then they also evaluated the agentic capabilities. So they said agent datasets included Terminal Bench 2, SWE Verified, SWE Multilingual, SWE Pro, Browse Comp, and the public evaluation set of MCP Atlas, and GDP File AA, and Tool Decathlon, right? So those are the data sets that were used to actually do the evaluation. So here are the results itself. So you can see that with DeepSeek V4 Pro, it generally wasn't the best performing model, which you expect because you expect the models from OpenAI and Anthropic and Google, those closed source models from those big labs to be the best performing. But you can see that across a couple of the benchmarks themselves, the DeepSeek V4 was really competitive with all of these large model labs. And so you can tell that although it isn't as good as necessarily the ChatGPTs and the Claudes and the Geminis of the world, it does perform in a similar range to those models. And yeah, so then they also benchmark the DeepSeek V4 Flash versus the V4 Pro models across each of the reasoning capabilities. And this wasn't really to show which does better, because as expected across the majority of these tasks, the DeepSeek V4 Pro Max does perform the best. But this is just more so to show that the performance of the models at each of these reasoning capabilities across a broad variety of benchmarks. Yeah. And yeah, so those are essentially the most important takeaways from the paper. So they talk about the performance on real-world tasks. So they say that standard benchmarks often struggle to capture the complexities of diverse real-world tasks. And they say that this creates a gap between test results and actual user experience. So they say that they developed proprietary internal metrics that prioritize real-world usage patterns over traditional benchmarks. And this approach ensures that our optimizations translate into tangible benefits. If you guys would remember when Llama 4 came out, Llama 4 performed really well on all of the benchmarks, but in real world, like when people actually used it, like nobody liked it. Um, so I guess DeepSeek did this to make sure that this didn't happen to them. So the tasks that they optimized for were Chinese writing, um, because they are a Chinese company, and search. Um, so Chinese writing, search, white collar tasks, which would be stuff like accounting and um, I guess yeah, stuff like that, like doing taxes and um, all of that stuff, like information gathering, document generation, document editing, etc., like knowledge work essentially. And they also evaluated them on coding agents. So is this it? Yeah, so they benchmarked themselves on Chinese writing, on their search capabilities, on their um, coding agent performance, and on white collar tasks, so knowledge work generally. But yeah, that is essentially the paper. That is um, what I think is the most important parts of the paper. Um, so yeah, um, I realized that I was just talking for a really long time going through this. I guess does anybody have any questions?
Well done, Jordan. Excellent review of the paper. Do you have like a couple of key takeaways? You sort of, we reviewed the paper at length, but to summarize it in maybe 2 or 3 points, what do you think is it, or the key takeaways in here? Did you see any reason, for example, why more American companies are would benefit from going to this model, this DeepSeek model, rather than uh, other than just for the cost savings?
Um, well, I guess to address the second part of your thing first, um, I don't think that, well, I'm not sure. I think that, well, DeepSeek releases their models openly, but they also release a really detailed technical report. So there's nothing stopping these American companies from just using the techniques outlined in DeepSeek. But um, like, I think that, so with Cursor, for example, Cursor, with their most recent coding model, what they did was they used one of the pre-trained models from a Chinese company. They used the Kimi pre-trained model, and then they did their post-training. They did a bunch of post-training on it to increase its effectiveness on code, like as a coding agent. So we may end up seeing like companies in the US using DeepSeek as a base, because it's open source, and it seems pretty competitive with the closed models, and then fine tuning it um, to their own use cases. So that it might be possible. I don't think there's anything stopping it from happening. Um, but there's also nothing stopping people from using the DeepSeek techniques to train their own models. Um, so to answer the first part of your question, in terms of like key insights, I think that some of the most important things that this paper spoke about were that um, as you scale the amount of data that the models can handle, it becomes more and more important to compress the attention. So I don't think that the from this paper at least, it doesn't seem like the dense token level attention that was used in earlier transformer models will scale to future systems that have these super long contexts. And the next thing um, is that I think that um, long context is probably where the entire industry is going. So um, if you so I'm not sure if you're familiar with the bitter lesson, but it's essentially the principle that um, techniques that in AI, techniques that, well, not necessarily in AI, but just the general principle that techniques that scale with computation will eventually outclass techniques that don't. Um, so with earlier models like the GPT-3s, the GPT-4s, if you wanted them to be useful for tasks, you had to build a bunch of scaffolding around those models so that they could actually process the things that are happening around them. But with these models with super long contexts, like the million token context length, I think Gemini has a 10 million token context length. Like those models, now that they can process like these super long contexts efficiently, um, they don't need to have all that scaffolding around them. The model itself can do all of the reasoning over the task. So it's these like this really efficient models kind of start consolidating everything into themselves. And yeah, I think those are the two main takeaways from the paper, in my opinion.
Thanks. Very interesting. I really appreciate it. Great job.
Yeah, just to add on that, I mean, it's clear from the paper that DeepSeek is prioritizing efficiency over anything else. And just the techniques that they use to try and compress the context, very interesting. And it's actually a bit surprising how they got that to work, being able to compress it that much, but it still relatively performs pretty, on par with some of the top models out there is very interesting. But say, I mean, I guess we didn't go into that part, but they did actually a lot of work also in like writing custom kernels, so that these things could run better on the GPUs. Um, One of the things like on the whole China versus US points, I did read an article saying that there are a lot of companies in the US, they're reconsidering their token budgets because basically they're spending a lot of money on these LLMs like Claude. And some of them or some of these startups have been, switching over to the more cheaper APIs. So DeepSeek, I know, hosts their model, and the token costs are way cheaper than the other LLMs like Gemini and um Claude and whatever. So I mean, I think their approach seems to be more looking at efficiency and being budget conscious, versus maybe American models that are more tuning for like peak performance, like getting the highest in benchmark scores and stuff like that. I mean, I think the good thing is like companies like Google that are um, re re-engaging the open source community by releasing models like Gemma. They released Gemma 12B the other day, which was pretty good. Um, but yeah, I think you know DeepSeek. I mean, even though it may not necessarily be the best open source model out there now, I mean they have a lot of competitors on that front, especially from China. I think what they did with that first DeepSeek really opened up the market for open source models to compete in the LLM race. And a lot of their techniques that they've put out there have actually been used by some of these American labs. So it's interesting that China somehow ends up being the country that's doing the being open um versus the States, but It is what it is. But I guess there is a economic play there in terms of um going the open source route. It kind of removes the moat that a lot of these companies like OpenAI and the Anthropic would have started out with, which, I guess it can lead into a whole discussion about the profitability um theory of these LLM companies. Is it actually going to be profitable? A lot of them are doing IPOs this year. With the amount of money they're spending on compute, is there room for profitability? That's still up for question.